continued. At least it is for me. You might have more. You might have had more space in your notebook, so you may not have to write that necessarily. Our second type of IMF is called dipole-dipole. Dipole-dipole. And what is a dipole? It's just a partial charge. Let's go to the right. Oops. Dipole. It's a vocabulary term. What is it? It's just a partial charge. That's all. Okay, so dipole-dipole happens between all polar molecules. Okay, let's go and do an example. I'm gonna pause so I can draw the molecule, and then I'll. Okay, that was just to save some time, but you can go ahead and draw these two molecules. You can pause the video if you need to. And dipole-dipole interactions, well, let's go ahead and assume, again, this is the strong molecule, right? So it's hogging the electron, so it's going to have a partial charge, and we call that partial charge a dipole, okay? It's going to have a partial of minus, right? It's going to have a partial negative charge. We call that partial negative charge a dipole. Well, if that's the case, then these guys all must also have partial positive charges. And the same for this one. These are all partially positive, right? And that'll be a partial negative. Well, just the same way the hydrogen bonding worked, these dipole-dipole interactions also work. In fact, hydrogen bonding is just a strong dipole-dipole interaction, okay? So let's say works the same way as hydrogen bonding, but not as strong. We can just say it's weaker. Yeah, hydrogen bonding is just a special case of dipole-dipole interactions. Okay, so it works the same way, it's just weaker. And this happens again between all polar molecules. Now you got to remember, not all polar molecules contain hydrogen, right? These guys don't contain hydrogen. There's a lot of them that you can go back in our examples and look that don't contain hydrogen, but they are polar nonetheless. And those that are polar that don't contain hydrogen fall under this dipole-dipole interaction. Okay. Okay, the third and last IMF is called London dispersion, sometimes called van der Waals. London dispersion. Weakest of the three. Let's just say happens between all molecules. It happens between all molecules, okay? But it's especially, you can see it, obviously, if it's the weakest of the three, then what's going to overtake it? Well, hydrogen bonding first, and then dipole-dipole, so it might not be as observable, let's say. But it happens between all molecules, but it especially happens between nonpolar molecules. Okay, it's the only one you can observe between nonpolar molecules. Okay, and why does it happen? The reason is because the electron, so the electron is never completely evenly distributed, even in, let's say, O2. Sometimes it's going to be on one oxygen a little bit more than it's going to be on the other oxygen. And because of that, it's never completely even. And as a result, there's always going to be a teeny tiny bit of a charge. It's like that tug of war where it might be going, you got two evenly matched opponents. It kind of still, that flag is in the middle, is still going to go back and forth a little bit, right? And you can think of it that way. So the reason is because It's never 100% evenly shared. There's always going to be a little there's always a little charge. Okay, so some examples of these include examples. Well, you can just think of the nonpolar molecules. The easiest ones to think about would be like O2. Right? O2, which would be like this. It's mostly charged, but every once in a while there's going to be a little bit of a, I mean, it's mostly neutral, but every now and again there's going to be a little bit of an uneven charge, and these things are going to interact. This other one's going to interact with this other O2. Okay? Every now and again. Cl2. Okay, Cl2 would be another example, right? This is a tug of war that's evenly matched, but every now and again there might be a little bit of a charge. And I can draw these molecules the same way. It doesn't, you know, for our purposes, they're going to look the same. It's a O2Cl2. And then the last one might be CH4. Hey, CH4 is one of those where you might have to think about it a little bit, right? Because you go, oh, this one comes up all the time, like we discussed in class. It comes up all the time. But it's also nonpolar. So is there going to be an interaction between other CH4 molecules? Yes, there will be. That interaction is going to be very weak. Excuse me, it's going to be very weak, and it's going to be a London dispersion force. So in order, ranking them in order of strength, strongest to weakest is going to be hydrogen bond. Is greater than dipole-dipole. Which is greater than London dispersion. Strong to weak. Okay. Final notes. Hydrogen bonding is not an actual, it's strong, so that's why they call it a bond, but it's not an actual bond between the two, between the atoms in the molecule. Remember, it's an intramolecular force. Okay, it's an intramolecular force. So don't make that mistake. It's not an actual bond. All right, it's an interaction between two or more molecules. And yeah, I think that's it. I guess we could just do this too, okay? We could say, we could put the examples in here. H2O, NH3, and HF. Dipole-dipole might be all polar. And again, London dispersion is going to be all molecules, especially nonpolar. Okay, there you have that. That concludes notes 7.3, part 2.